Hello everybody. The lecture today is going to talk about linear regression in a little bit more detail. Specifically, we're going to talk about the hypothesis testing and inference associated with some of these regression details. We're also going to work with Excel's data analysis tool pack. This is an add-on, and we'll talk about how to add this into your Excel workbooks. But we're going to run some regression analysis using this analysis tool pack, and then I'm going to tell you how to interpret this voluminous output that you're going to see when we run this regression. Let's get started. So if you haven't already seen these videos, inside of your slides, these two things are links, so you can click either one. And it's a video that'll walk you through how to add the data analysis tool pack, which we're going to use a little bit later. So you can click this either for PC users or for Mac users. I recorded the Mac users, somebody else recorded the PC users. So make sure that you watch those videos if you haven't yet to have your data analysis tool pack. And this isn't a typo, there's no C in tool pack. Make sure that you've added these before you kind of continue on for the rest. So pause the video, make sure that this is ready to go. Okay, so now that we have the data analysis tool pack loaded, and this by default should always be loaded in your Excel workbooks from now on, but just in case for whatever reason maybe you reinstall Excel, keep in mind that the links are right here in the slides if you need to re-add your tool pack. Today's primarily going to be example based, so I'm going to walk you through running a regression analysis using this tool pack. These are the steps listed. Inside of the data ribbon, we're going to go to the data analysis button. A dialog box will pop up and we'll see an option to choose regression. Just like we select X and Y ranges as we're doing some other things in Excel, like adding plots, we're going to input an X and a Y range for our regression data. We'll set a confidence level, and we'll talk about why we need to do that in a little bit. And then there are some other checkboxes I want you to put down: residuals, residual plots, and normal probability plots. Okay, so let's go to an actual workbook data, and I'll show you how to run this regression analysis inside of Excel. So I'll walk through these steps, but they're here for you if you need them. All right, so in your week 13 materials, you'll find an Excel workbook called W13D2. And if we open up that Excel workbook, we'll see our first data set here. The worksheet's called HRT-RT, shortcut for heart rate. And what we're looking at is two variables. One is the age of the person, and the other is their maximum heart rate. And we can see that essentially each row would correspond to a person on which we've measured their age and their maximum heart rate through, I don't know, maybe a treadmill test or something along those lines. Okay, so what we want to do is we want to run a regression analysis. Now, keep in mind, just because we have this regression, this data analysis tool pack, doesn't mean we should forget about our other tools. So for example, we can always insert a scatter plot to get a look and feel for our data. And inside of those plots, we can add trend lines. And through the trend line options, we can make sure that the equation and the R-squared value for our this linear regression are right on top of that plot. Maybe I'll move this here actually. And we can do other things. We could get the Pearson correlation coefficient. Remember using our Pearson command, B3 to B44, A3 to A44. So we have a negative correlation here. So it seems like the older you are, the lower your maximum heart rate. Magnitude-wise, it's pretty close to 1. So this is a relatively strong correlation. And we can see that by the dots nicely following our regression line pretty closely here. Okay. Now, what we want to do is sort of layer in some extra information. So one thing that we've talked about already is determining whether our Pearson correlation coefficient is what we call a significant correlation. In other words, at the population level, does the data here in the sample Pearson correlation coefficient we computed, is that different enough from 0 to imply that at the population 0 we have a non-zero correlation? In other words, there is at the population level a significant relationship between these two variables of age and maximum heart rate. Now in the past, we've had to open up a separate workbook, plug in our Pearson correlation coefficient, plug in our sample size, something else we can compute here, just do count, pick one of your variables, in this case 42, and then the workbook did everything else in the background. So this is an example of an inferential statistics application to this correlation and linear regression approach. Okay? So what I want to do before we actually run our regression analysis is I want to remind you of why we need some inferential statistics when we're doing these types of regressions. So our setup for a linear regression or a correlation is the same as the setup that we've seen for our other types of inferential statistics techniques, right? When we're estimating or doing hypothesis tests for claims about a population mean or a population percentage. The idea is that in theory, one could access the entire population of data. So we could collect, say, the heights and the weights of every person in the United States. And at that level, having all the data, having all the population data, we no longer are dealing with statistics, but parameters. And so correlation would be a population level parameter. And we could have a best fit line as well. And that best fit line would have a certain slope and an intercept, and those would be population level parameters. But we don't actually do that. Remember, we primarily work with samples, which is where you take a random collection from the population, but we're only looking at a part of the population. And what you can see is that just visually, as you collect different possible random samples, there's quite a bit of variation in the red line, which is the regression line based on the sample, right? And there's a few things that are changing. There's a few things that are updating. All three of them I've listed here. We've already talked about how the correlation on the sample might be a little bit different than the correlation at the population level. And this is why we talked about the significant correlations versus non-significant correlations. It involved a hypothesis test where we looked here and said, is this sample statistic different enough from zero to suggest that at the population level we have a non-zero correlation? But now we're going to extend this to something even more. We're going to extend this to looking at inference for both the intercept, which is where this red line intersects the y-axis, and more importantly, the slope term, which is the slope of the red line, right? The regression line based from the sample. Right? We know that we have a population level slope and a population level intercept, but when we only look at a sample of data and build our regression line from that, we're going to see slightly different values for both the slope and the intercept. So we can do inferential statistics at that level as well. Right? Can we say, based on this sample slope that we get, our estimate for that population parameter, can we say that that's different enough from zero that our slope is truly non-zero? We can even build confidence intervals that tell us, based on this estimate, what range we expect that population level slope to fall in. So all of the things that we've been working with so far, hypothesis testing and confidence intervals, can actually be applied to correlation, to the intercept for your regression lines, and to the slope terms for your regression lines. And again, just what the visualization is doing here is it's selecting at random from the population, and in red you see the sample that you've selected, and the red line represents the regression line built from that sample information. And what you see in the table here is that as you're selecting new samples, it's computing the sample correlation, the sample intercept, and the sample slope. And you see that they vary quite a bit away from the actual population level parameters. We actually see quite a wide swing in the intercept. The slope and the correlation are a little bit more stable. But this is why we need inferential statistics, because even when we're doing regressions, we're only looking at a sample from the population. So we need to we're going to want to say something at the population level. And in order to do that, we need to use inferential statistics, so hypothesis testing and confidence intervals. And that's what the regression tool pack is going to help us do. It's going to do a lot of those computations in the background so that we just have to read the output and sort of interpret it. Okay, so with that reminder of why we need inferential statistics, even though we're talking about a new technique, linear regression, right? We can start to think about why we would want to, for example, run a hypothesis test or possibly a confidence interval for a correlation coefficient, or similarly for the slope terms and the intercept terms for this regression line that we've created based on data from a sample rather than all the data we would get at the population level. Now, we could walk through, how do you find the test statistic, what's the right probability distribution, et cetera, et cetera, et cetera. But hopefully you're getting to the point where you're ready for Excel and technology to do a little bit of the heavy lifting. This is exactly what the data analysis tool pack is going to do. So as a quick review, remember, running a regression analysis is always going to follow these 5 steps. We're going to go to the data ribbon, select the data analysis button, and then run our regression. And then we're going to input our X and our Y values. We're going to set our confidence level, and this is the confidence level for our confidence intervals that we're going to generate. And we're going to select some diagnostic plots, which we'll talk about at the end. So here's how we do it in Excel. Remember, we go to the data ribbon, and all the way to the right, when we were checking to make sure that this pack was installed, there's a little button that says Data Analysis. You want to click that. And this will look slightly different on a PC, but hopefully largely the same. We have a lot of different analysis options. We want to select the one that says Regression. They're in alphabetical order. Hit OK. And we'll get a dialog box that looks something like this. Now, notice that the Y range is first, so you have to put your response variable or your vertical axis variable, in this case the heart rate, first. So the way I like to do this is if you click these boxes in the corner, this thing kind of zips up, and you can use your keyboard shortcuts or you can highlight, etc. I'm just going to do a Control-Shift down, and then if you click back to that corner, it'll bring you back to the original dialog box. So you can do that. You can also type out if you want, if you know the range A3 to A44, you can also type out what your X and Y ranges are. Now, in the background, they're automatically going to run some confidence interval estimates for our slope and our intercept regression terms. So we can set a different confidence level if we want. So just to practice, I'm going to click this confidence level box, and I'm going to say I want confidence levels of 97%. In terms of the output options, I think it's always a good idea to put your regression output in a new worksheet. So click that middle dialog box and say heart rate regression. Give it just a name that clearly identifies what data set you're working with, and then that it's a regression analysis. Now, as far as the things we want to look at, there are some residual plots diagnostic plots we'll want to look at. Residual plots, normal probability plots, and I'm also going to have you click the residuals for now, just to show you this. Standardized residuals are sometimes good to see too, but we won't talk about that in this class. So once you have your entire dialog box set up, you can hit OK. And Excel is going to take a second to compute some stuff. And you'll notice that you now have a new worksheet labeled Heart Rate Regression. We have 2 plots. One's what we call a residual plot, and one's a normal probability plot. We'll get to those later. For now, I'm going to zoom in. And I want you to notice that we have 3 tables. We have a regression statistics table, we have an ANOVA table, and then we have what I'll call the coefficients table. Down below, we have the predicted Y values. These are your Y hat values for each one of the observations in your original data. So row 1, this observation of 66, 146. The predicted value through the regression line's a 151 for the heart rate, and this is how far they were off. The residuals are just the errors, so we talked about that already. But primarily when we're looking at the regression analysis, we're going to pull information from the regression statistics table and the coefficients table. So that's what I want to walk you through next. The way that we're going to do this, I'll sort of bounce over to the slides and talk about each one of the terms, but then I'm going to jump back into the Excel workbook, and I'm going to sort of erase some things or sort of, I guess, change the color so that they're not as easy to see, and we're going to leave ourselves a lot of comments as well. And the goal here is that once you have one of these regression analysis outputs all marked up, if you do this 2 or 3 more times, you'll really get a feel for what you need to pay attention to and what you can primarily ignore when you're looking at your regression analysis for this class.